All right, so hopefully you already watched the video on the geometry and nomenclature and have a sense on how the tooth geometry or the profile is generated, as well as how we calculate the forces on the gear tooth. Next, we need to use those forces to be able to calculate strength as well as fatigue. So that's what we're going to do in this one. So in this slide, we have a photoelastic pattern of stresses on a spur gear. So they can apply like the special coatings, and then it changes the way the light kind of reflects from the gear tooth. And basically from these type of, I guess, pictures, what we can tell is where the highest stresses are. And so wherever you see this, like these lines kind of meet together, where's my laser? Hold on. Wherever you see this line come together, it means that likely there's very high stresses. And it makes a lot of sense. What do we have over here? We're gonna think of this gear tooth as a beam here in cantilever, and there's a force being applied. So right at where the force is being applied, we're gonna have, you guessed it right, contact stresses, right? And then at the very bottom over here, the force is here, so the moment is highest, right at the base. So basically at the base or the fillets, we're gonna have bending stresses. So we're gonna look at the two. Here we go. So first one is contact stresses in the gear tooth. I have an example, but actually I cheated, like my son says, and I already covered contact stresses. So I'll go ahead and link a video from the chapter on the surface damage, which I think was chapter 9, which covers exactly this example. But hopefully now it makes more sense of why we were covering contact stresses and the gear teeth. Essentially what we're doing is we are treating the tooth of the gear, because remember these guys are in 3 dimensions like so. And we're actually treating them as cylinders, like if there was one cylinder like this in contact with this other gear tooth, this other part is treated as another cylinder. Hopefully that made some sense when I explained that video. Anyways, contact stresses, there's an easy way and there's a little bit more involved way. I'm only going to cover the easy way, which is through this example, again, on a separate video. So now let's look at bending stresses. So again, basic analysis of gear tooth bending stresses. We're going to go over the Lewis equation. It's just a famous equation for bending stresses in gear tooth. And this equation was developed by Wilfred Lewis. That's why it's called Lewis. And it was presented in the Philadelphia Engineers Club in 1892, a while back. And so here's what some of the assumptions that are going to come into this Lewis equation are. The first one is that the full load is going to be applied at the tip of a single tooth. Again, remember, we're considering that tooth as a beam in cantilever, right? Where's the worst case scenario where if let's say the force is constant, where would it make the highest bending? Well, the furthest away over here. So that's the first assumption. It's the most severe care, but usually it's not the case, because the contact ratios are usually more than once, which means usually the load is shared between at least 2 gear tooth. Anyways, the assumption is only one, just to make the analysis simpler. Next is that the radial component, remember, which is this one over here, is going to be negligible. And why does that matter? So let's look at my ugly drawing here at the top. If I have a force pushing sideways, right, this is going to cause the beam to kind of bend in this direction, which would put this part in compression and this part in tension. Well, the force is not just tangential, it's also radial. So there's a component that pushes down, which is going to compress back up. Well, in the Lewis equation, that component is completely neglected. So it's giving a more conservative approach. It's predicting higher bending stresses than there actually are. Again, because the combined loading is going to tell us that we're going to have some compression here from the radial and then plus some bending, right? Anyways, number 3 is that the full load is distributed uniformly across the full weight of the tooth. So remember, when we have a tooth, it's actually always in 3 dimensions. So this guy really looks something like this. Whoop, like so. And what we're saying is that the load here, we draw it right here, but in reality, we're saying it gets applied through the full width. So this is assuming like perfect machining and perfect aligning. Usually that's not the case, but for the derivation of this equation, neglect it. So that was number 3. Number 4 are the forces due to the tooth sliding are negligible. As the tooth are sliding, there's going to be some forces in these, these direction here. Well, this Lewis equation, going to ignore that. Number 5 is that the stress concentration of the tooth fillet is negligible. So anytime you have a change in geometry, there's a stress concentration right here. Lewis just ignored it. Actually, the concept of stress concentrations didn't come till about, I don't want to lie, but it's going to be like 30, 40 years later, something like that. Anyways, this is ignored in 1892. I already covered this, sorry. Here we go. So we're going after the bending stress. Here's what the bending stress equation looks like, MC by I. However, when we're doing the bending, we're not considering, or what Lewis did is, it's not considering the full profile of this tooth. Again, we're considering that tooth to be like a cantilever beam. We're not oversimplifying it, so we're not thinking it of a straight beam, right? But we're also not considering that this is the cross section of the beam, like the gear tooth, like does something like this and like that, something like that. So instead, what we assume is we draw inside this constant stress parabola. So I don't know if they showed you this in solids, but what is a constant stress parabola? Well, if you have a beam that kind of looks like this, it means that the bending stress, if you apply a load here to cause bending, because the geometry, the cross section is varying and it starts very small over here and it gets bigger, what you get is that the bending stress is going to be constant throughout. So it's not going to be maximum at the base or less at the top. The stress is actually all the same. Anyways, the formula for the bending stress for a constant stress parabola simplifies to something that looks like this. 6 times Ft, that's the tangential force, times h, which is the height of the tooth, that's the height over here, divided by the b, where the b is the width of the tooth, that's this dimension here, the width, and then times t squared, which is the tooth thickness, this one here, t, that is t. Anyways, and then they do some mumbo jumbo here with some equivalent equivalent triangles. And they're going to basically rearrange this formula over here, substituting this on top over here. And they tell us that now the stress is just 6 times the tangential force divided by 4 times b, which is the width, times x over here. And then what they're going to do is we're going to come up with this Lewis factor, little y, which is equal to 2x divided by 3. So you're going to get 2x divided by 3 over here. And so substituting this into this one, we get this equation over here, that the stress is the tangential force divided by the width of the tooth times P times Y. Okay? Where little p is going to be circular pitch. Now, because gears are made of standard values, means they have standard geometry, diametral pitch can be used. We know that diametral pitch, which is big P, is related to little p by this equation. And then, so putting this one up here for big P, and then this expression for little y, which is just big Y by pi, This top equation can be written into this one on the bottom, and this is what we commonly refer to as the Lewis equation, which says that the bending stress is just equal to the tangential force times big P, which is diametral pitch. Remember, that is the quantity that we use to describe gears here in the US. It's the inverse of the module, which we use for SI units. Anyways, sorry. So that gets divided by a little b times y, where y is the Lewis form factor, and it's a factor that we get off of a graph. Little b over here is still the width of the tooth, so it's still this dimension over here. So I jumped the gun on the previous slide, but remember that the diametral pitch, big P, is related to the module. They're inverse of each other. So again, we can write the Lewis equation as on top over here for US customary units, or in SI units in terms of the module, like so below. Regardless of which one we're looking at, we can see from the equation that the bending stress is going to depend directly on the tangential force being applied, meaning the higher the force, the higher the stress linearly, so as expected. It's also inversely proportional to the tooth width B, so the wider the tooth is, right, the bigger the B, which is at the bottom, the smaller the stress, as expected. It's also inversely proportional to the tooth size P, or 1 by diametral pitch or the module, as well as inversely proportional to the tooth shape factor, Y over here. So next slide, we'll talk about this tooth shape factor. Figure 15.21 is where we can get the Lewis form factor or shape factor. It's going to be dependent on the number of teeth over here, and is plotted for various pressure angles. Now I have the pressure angle of 20 highlighted in yellow because usually that is the standard pressure angle. So basically, as we look over here, for example, if you're looking at a gear with an N of 30 or 32, you go up over here, and assuming it's the standard pressure angle of 20, right, and you come this way over here, and you would see that the Lewis form factor is roughly or very close to 0.35. Now, you remember the Lewis equation had a bunch of assumptions, about 6 or 7 of those, so we can actually further refine this Lewis equation to account for other things such as pitch line velocity. Again, pitch line velocity is anytime you have a gear and it's rotating, the pitch line velocity is how fast that point is moving. Of course, the greater the velocity, the greater the impact as teeth come in contact. Remember the equations for the impact factor. One was in terms of drop height, and then the other one was in terms of velocity. So higher velocities leads to higher impact. We need to capture that, and we will in a little bit. Also, manufacturing accuracy. The lower the accuracy, the more play there is between the gears, the less likely that the adjacent teeth are going to share the load. Again, if the gears are not very precisely machined, then really they're not sharing the load as good as they could. Next is contact ratio, and this is the fact that the load can be carried by more than one teeth. Remember, the Lewis equation assumes only one. In reality, there's always more than one. So for contact ratios between 1 and 2, what can happen? You can have half of the load at the tooth tip because it's shared between two, or you can have the full load at the highest single tooth contact, which is close to the pitch circle, something like that. For contact ratios between 2 and 3, well, you can have the load three-way division at the tooth tip, or two-way division at the highest point to double contact. Next is stress concentration at the base of the tooth. Remember, the tooth profile looks something like this, and we forgot to account for the stress concentration from that fillet radius. We'll show you how to do that in the next couple of slides. Next is degree of shock loading. So these gears are going to be connected to some equipment, and the equipment, like if it's a press or something, it might be receiving some shock loading. Um, we'll show you how to account for that. Sorry. Next is accuracy and rigidity of the mounting. So what can happen is there's any shaft deflection or misalignment from the shaft. This is going to lead to non-uniform loading across the full width of the tooth. Remember, the tooth have an associated width with them. So if the alignment is not perfectly parallel, instead of nicely having like an area line contact, it could kind of be more to one side than the other. Anyways, we'll show you how to account for some of that. And also for the moment of inertia of the gears and the attached rotating members, which could be the shaft or whatever, maybe the motor that the gear is attached to. And really what happens is when you have large inertias, these inertias are going to resist the momentary angular acceleration or decelerations, right? And so the bigger the mass, the bigger the, no, sorry, I shouldn't say mass, the bigger the moment of inertia, the more resistance you're going to have to changes, and this can result in momentary tooth loads as you speed up or slow down a gear. And this is more of dynamic analysis that can get very complicated very quickly. So here we have the modified Lewis equation for effective fatigue stress. So it's basically the Lewis equation. You can see some of it over here, but instead we have other factors which are going to again add the contribution of the pitch line velocity and all the stuff we covered on the previous slide. So instead of y, we have here a j. So this is a spur gear geometry factor. Remember, the Lewis has a y. Here we're using a j. We get this one from figure 15.3. And this is actually including the Lewis factor y plus a stress concentration factor for the root. Again, once we have the tooth stress concentration for these areas over here. These areas. A KV is going to be a velocity or dynamic factor. We're going to grab it from 15.4. And this is going to reflect the pitch line velocity and any manufacturing quality issues. KO is going to be an overload factor. We're going to use table 15.1. And this is to add the contribution from non-uniformity of the driving and load torques. And KM is going to be a mounting factor. Again, reflecting the accuracy of the mating gear alignment. This is from table 15.2. So next, the geometric factor J. Now, where does J go on the formula? Remember, it's at the bottom over here. So what does that mean? A bigger value of the J, right? A bigger number at the denominator means a lower stress. So here we have figure 15.23 where we can get values of J. Notice as we look on the x-axis, this is going to depend on the number of teeth on the gear. And it's given for two common pressure angles, the 20 and 25, which is also common, but not as common as the 20. Anyways, we see a bunch of lines over here. What are the different lines? We see grouped up on top, we have for sharing. So these are going to be for high precision gears. Only the high precision gears, or where the tolerance are very small, are the ones that we can guarantee that those contact ratios are going to lead to the load being shared by more than one gear tooth. If they're non-precision, I'm sorry, right? There's more slag, more play. We cannot guarantee that there's load sharing, and so that's why we have this load. No load sharing. This would correspond to the line here at the bottom for the 20 and for the 25 pressure angle. For the sharing one, we're going to see that it's going to depend on the number of teeth in the mating gear over here, right? So you would pick this factor based on the gears that you're analyzing. So let's say you have a pinion and then a gear. So let's say you're analyzing the stresses on this guy, right? You would count how many gear teeth are on that guy. You would go over here, But if it's a high precision gear, then you would also have to figure out what is the number of teeth on the mating gear, which would be on this guy. More or less pick from here a line and actually get the values. And what are the values, right? Let's say you have number of teeth on the pinion to be, let's pick an easy number. How about 30? Right, so you would go here to the 30. And let's say it's pressure angle 20 degrees. So you would come over here for 20 degrees. You would be at the 20. If it's a cheap gear, the quality is super bad, then you would be looking at a J factor of almost 0.25, so about 0.24. If it's a high precision gear, it's going to be more expensive, right? Then depending on the number of teeth. So let's say this one over here had about, I don't know, say like 50. So you would come over here for the 50 line, more or less right there. So that would put the J factor, oops, I went crooked, close to 0.34. Again, remember, a higher J factor on the denominator means that the stress is going to be lower. So that's another advantage for having high precision gears. Next is the velocity factor KV. So KV is going to depend on the pitch line velocity. Remember, we have the equation for the pitch line velocity. So you would come that for the gear that you're analyzing. And then depending on the manufacturing process for that gear, if it's high precision shave and ground, high precision shave and ground, highest, high precision, or just hop, shaping, and forming. These are just like as cut. There's no shaving or grinding. Same thing, you would, based on the pitch line velocity that you're using, and then the finish on that gear, you would come over here and you can see that the velocity factors are between, so the lowest is 1, you go 2 or 3, and notice all the way up to maybe 4. And what's it doing? It's over here, right? So these are actually amplifying or multiplying the stress, right? So here, high velocity factors are a bad thing because they are increasing the stress that the gear tooth is seeing. So next we'll look at the overload and mounting factors, KO and KM. We can see that these factors are multiplying or magnifying the stress, right? So these factors are going to be greater than 1. The higher the number, the higher the stress that the gear tooth is going to be on. So first let's start with the overload correction factor. This is looking at, excuse me, the source of power, if it's uniform, light shock, or medium shock, and then what is driving, if it's a uniform, moderate shock, or heavy shock. So what is, for example, a source of uniform power? This could be like an electrical motor, right? What would be light shock to medium? So imagine like a gear directly connected to like a two-stroke engine, like on a go-kart. It's getting, if the flywheel is not big enough, it's getting those impact loading from every time the piston gets the spark, right? Anyways, so you would go here, right? So let's say you have an electrical motor, but it's driving say like an impact wrench or something that is under heavy shock, right? So the power source is uniform, but it's driving an impact wrench. So that would put a KO of 1.75, for example. Next is mounting correction factor, KM. And this is going to depend on two things. One is the face width. Face width, as you remember, is the width of that gear tooth. So this here is the face width. The bigger the width, the more sensitive that the gear is going to be to misalignment. So you can see here face width in inches from 0 to 2 to 6 to 9 and even higher. We can see that as we go that way, all the factors, regardless of the conditions, they're increasing, right? So the face width is going to play into it. And then what else is going to play? Well, the support. If you have accurate mounting, small bearing clearances, minimum deflection, high precision gears, all right, you're going to have low factors. But as you go with less rigid, less accurate gears or crappier bearings, then you can see these numbers as we go down, they're going to be increasing. So the previous equation, and with all those factors, we use it to calculate the stress on the tooth, the bending stress, right? If we want this gear to last forever, we need to make sure that those stresses never do exceed the endurance limit of that material, right? Of the endurance limit of the materials that the gear is made up of. And so we can calculate what the endurance limit is specifically for the gears by using this equation, which looks a lot like um, the endurance limit equation, but it has some factors, additional factors here, or slightly different ones for specifically for the gear application. So let's go by one. The first one, Sm prime, is the same one as when we did the fatigue chapter. This is the standard RR more endurance limit. If you're working with the metal, usually that's going to be 0.5 or 50% of the SU, or the ultimate tensile strength. Next one is the CL, which is the loading factor. Because the gear tooth are loaded in bending, this is going to be equal to 1. Next is going to be a gradient factor. So here the gradient is going to be measured in terms of the diametral pitch, big P. So it's going to be 1 for P greater than 5, or 0.85 for a big P less than 5, less than or equal to 5. Next one is going to be a surface factor. We're going to use figure 8.13, which is the figure that we use for calculating surface factors in the fatigue. Now, usually the gears are going to be machine surfaced. Next one is going to be KR, reliability factor. So it's very similar to the one from fatigue, but we can use table 15.3, which makes our life a little bit easier. KT is like the temperature factor. Here is going to be equal to 1 if the gear, or maybe if it's under a transmission, if that gear oil is less than 160 degrees Fahrenheit, then you just use 1. If it's any higher, any temperature higher than 160, that's the equation that we use. And then the last one we have Km, which is the mean stress. So here it's going to vary depending of if we're working with an idler gear or if we're working with an input and an output gear. Now, why does the mean stress vary? Hopefully you remember our example where we had the pinion gear and it was driving the idler gear and then the output gear, right? So as you remember, the pinion was putting a load in that direction while the output gear was resisting and it was putting in the opposite direction. So if you can imagine, if we look at the gear tooth, if we look at the scenario 1, when the gear tooth is right there and we're looking at the idler, so I'm going to draw it, it's going to look something like this. There's a force pushing that way, right? And if we follow that gear tooth as it rotates, and now it's on this position over here, so it's the same one, and now it's rotated kind of like so. Remember, first it was being pushed over here from the bottom, which is that way, so it was being pushed like so. When it reaches the output gear, it's resisting, so it's pushing on the other side. So what just happened here, right? The gear tooth on the idler saw it load from one side, and then from the other, it just went to a complete reversal. If we just look at the gear tooth on the pinion, so let me draw it over here. Let me say the pinion is green, right? Every time the pinion is applying the load to the idler this way, right? So what does the pinion's gonna feel? It's gonna feel the equal and opposite. But because there's nothing else, it's always gonna feel the load in this direction, only one direction. So the mean stress, I'm jumping the gun here. So the idler sees bending on one direction and then to the other, it's worse. The input gear only sees it from one side, and that's why that mean stress factor is 1.4, right? Here, look at the difference. A bigger number is gonna give us a higher endurance limit. It means that it can take a higher stress without failing endurance limit. Okay, so we covered most of the factors on the previous slide. Remember one of the factors was the surface factor. This is the same plot that we were using for the fatigue chapter, I believe chapter 8. Don't, yeah, look at this, chapter 8, good memory. Yay. Anyways, so the gears are usually are in the machine state. So you would be using this line over here. No need to go as hot roll, as forge, and all this other stuff. So basically, you're always kind of looking at this one, right? So you still would have to determine what are the properties of the gear material, tensile strength, and then depending on that one, you go up a value, and then that would tell you what surface factor to use. And the other one is the reliability factor. So here is for different percent reliability: 50, 90, 99, 99.9, 99.99, 99.999. Anyways, you get the point. Look at what's happening to the reliability factor. As you want more and more reliability, these numbers are going smaller. So effectively what it's doing, right, because it's being multiplied, it is reducing the endurance limit or the allowable stress that we can put on this gear tooth so that we get an indefinite life, right? So once you calculate the two, once you have the endurance limit from the previous slide as well as the bending stress from the kind of modified Lewis equation, you can divide the endurance by the bending to strength, and hopefully the endurance limit is much higher than the stress that the material is seeing, right? So this guy is much higher, and if it is, then you're gonna get a value better, higher than 1, and this is what we'll call the safety factor. And I just put these um, dumb letters over here, so just to indicate that this would be the safety factor for the tooth bending fatigue. So I'll just say it one more time. We have the modified Lewis equation. We can figure out the stress on the acting on the tooth, and then we can use the modified fatigue equation to figure out the endurance limit or the endurance strength. So we divide the strength by the stress, and it's going to give us a safety factor. Typically, you're looking for a safety factor of at least 1.5 when you're using a KR or 99.9% reliability. That's good enough. Again, because you're already accounting for reliability through the KR constant, we don't need to have overly crazy safety factors like 2, 3, 4, 5. 1.5 is enough, again, because we already have some built-in reliability. And I believe that is it. Let me see. Yep, that is it. So hope you like that one.